All right, let's do one last example from section 10.8. This is problem 22. The sum from 1 to infinity of n factorial times x plus 2 to the n power. You'll notice that sometimes as math teachers we're a little bit lazy. When we write the summations, we just put the limits here. We don't actually write n equals 1 to infinity. It's relatively common for people to do that, so I just wanted to mention it in case you noticed it. All right, so once again, we'll use the ratio test. We'll see what it gives us. And then once we're done with that, if we need to, we'll check the endpoints to see whether the series converges at either or maybe both of the endpoints. So once again, I need to calculate a sub n plus 1 and a sub n. A sub n is just what they gave us. That's n factorial times x plus 2 to the n power. Again, to get a sub n plus 1, every place there's an n here, I'm just going to replace it with n plus 1. So I'll have n plus 1 factorial times x plus 2 to the n plus 1 power. And go ahead and simplify. N plus 1 factorial is n plus 1 times n factorial. X plus 2 to the n plus 1 power is x plus 2 to the n power times x plus 2 to the first power. As always, when you multiply these, you add the exponents. So we need to look at the limit as n approaches infinity of this thing, n plus 1 times n factorial times x plus 2 to the n times x plus 2 divided by this thing, n factorial times x plus 2 to the n. And let me say again, I'm leaving out the absolute values until the end of the problem. Professor Mitchell carries them through. As we mentioned to you, it doesn't really make a difference which way you do it. Do whatever seems easier to you. Notice the n factorials cancel, the x plus 2 to the n's cancel. X plus 2 comes out here because it's a constant as far as n is concerned. But as n goes to infinity, n plus 1 also goes to infinity. Notice that that's greater than 1. So this particular series diverges. And in particular, we do still have to maybe check the endpoints that would make this equal 0. That is, if x equals negative 2, this would be 0 to the n power. So the series would just be 0 plus 0 plus 0 plus 0. So technically, the series will converge for just this single value of x, because you'd end up with the series 0 plus 0 plus 0. But that's the least possible interesting series we can think of. We don't really care about the series 0 plus 0 plus 0 plus 0. So technically, this series will converge if x equals negative 2, but it's pretty much a useless series in that case. So this is an example where the limit is greater than 1. We wanted to make sure we did one example like that, and in general, the series diverges.